Hello and welcome to our ECE 106 design project. So our design idea. We wanted to create a set of touch sensors using capacitors to interact with other computers, with a computer to play Tetris. The circuit was created using Arduino breadboard and parallel plate capacitors created from aluminum foil sheets. So measuring the capacitance. So we know the formula for capacitance, which is C equals epsilon A over D, where epsilon is the dielectric permittivity, A is the cross-sectional area between the plates, and D is the distance between plates. So basically, our finger, when it touches the capacitor, is the other end of the capacitive plate that connects to ground, which is illustrated in the diagram right here. And so when our finger connects with the capacitor plate, it becomes close enough to basically mimic a capacitor, and in which becomes itself a capacitor. And from there, we can sense touch. Now, measuring the capacitance. Here we have the voltage equation for a capacitor, or just for the circuit in an RC circuit. And so, given the time constant, which is tau equals RC, when t equals tau, we end up with this expression right here. And so from this, we see that we want to find the final voltage, which in our case is whatever is being sent off, times 0.632, which is basically 63% of the voltage we sent, which in other words means we want to measure the time it takes for the capacitor, or at least the other end of our circuit, which has a capacitor, to charge to 63% of the voltage. And from there, we can determine the fact that the capacitor has been touched, and thus use it in our program. So in our circuit design, here we illustrate from pin 2 to pin 4. Pin 2 sends a signal at 16 megahertz, which will become important later on. It passes through a resistor of 1 mega ohm, and through this capacitor, this end is basically our finger in this situation, and pin 4 will measure the time it takes for the capacitor to charge to 63% of the voltage. And so here is our complete circuit with all 4 capacitors that we used, all in parallel. Here is our circuit design with your Arduino board with all pins and all capacitors connected as well. So from here, when we detect a capacitor to be touched, and from that we can tell how long it has been touched for. And from that time that we've measured, we can then later use it to send a key press to the computer in order to play or to do anything on a computer, such as play Tetris. So in building the sensor, we use 4 aluminum sheets folded into a radius of 0.3 meters, basically 3 centimeters, 4 resistors, all in 1 mega ohm, and 1 Arduino Uno R3 microcontroller board using the AT Mega 16U to core processor. So looking at the equations for capacitance and time constant, which are right here, C equals epsilon A over X, where X is our distance of the finger to the capacitor plate, and T equals RC, where R is the resistance, which is 1 mega ohm, and the capacitor. Combining these expressions, we get the expression T equals R times the expression for capacitance. So with this, we now see how the tau is proportional to capacitance. So as capacitance increases, basically as our finger touches the capacitive plate and becomes a capacitor, our finger comes closer to the capacitor, we then are able to determine that tau becomes larger. And from that, we can determine when the time gets larger, we will send out a key press signal to the computer, which can later perform actions such as play Tetris. So looking at our code, here we import some libraries that we are using to detect the time. And here is just some code for the LCD screen that we will use in our demonstration later on. Here we declare, basically here I'm declaring the capacitive sensors registered at the pins that we have on our board. And here is also basically for the LCD screen and to send out in order for our key press signal to act as an actual key press. Here's a buffer that will actually send out our key press signal. And this void setup here, we basically set up our LCD screen and also our graph that we will later show in our live demonstration. And here are our variables that we declare to detect the total time it takes for each capacitive pin to reach 63% of the voltage. So we detect it, we want to find it for W, the key W, A, S, and D. So just looking at W, we see that when we detect the time basically above a certain threshold, which we can which we can set at any rate, giving it the key code of W, and this is basically just code for our LCD screen, we can later send out a buffer and basically send out a signal for a key press. And this key release function basically completes the signal and tells it to only generate one key press. And this is other code for our LCD screen. And this is for our graph that we used in our live demonstration. And we see this is the same for all of the other keys. So A, S, and also D. And this is the key release function or release key function that we use to complete the key press signal. And so from measuring if our time that we calculated or measured to be above a certain threshold, basically when capacitance increases, the time will increase. So once that time is above a certain threshold, we are then able to tell, okay, so this capacitor has been touched, and thus we must now register it as a key press to W, A, C, A, S, or D. And this will now all be shown in our live demonstration.
Alright, so I'm here today with the live demonstration of our capacitive touch sensors. And we have 4 sensors which correspond to the W, A, S, and D keys on a keyboard. And as you can see, if I just hover slightly over them, there isn't much notice until I press the capacitor. And you can see the value of the W increasing. When I touch the A increases. When I touch the S increases. And when I touch the D increases. And now you might see some other values changing, and those are fringe fields because they're so close together. And this is important to take note of, but when compared to the actual values, you can see that they're pretty negligible.
So calculating the overall sensitivity for the capacitor, basically, once again, we look at the equations for capacitance and the time constant, which are given here. C equals epsilon A over X, where X is the distance of our finger to the capacitor plate, and T equals RC, where R is the resistance and C is capacitor. So we take the derivative of both. We get the two expressions right here. And then later, combining them and putting them in terms of dx, we see that in order to we get an expression for how much we can measure in the change of our detectance distance, basically, to the capacitor is given by this expression right here, which is dt, the change in time, so the change in time, and x, which is also the distance of the capacitor, and epsilon, a, and r, which are all defined as before. Now in this, as mentioned before, this measures basically how much in change in the detector we can detect, dependent on these variables right here. Most importantly is dt or d tau, where if we realize that we are sending a frequency out at 16 megahertz, the smallest value, or I guess snippet of tau, can be 1/16 millionth, basically. So setting dt to 1/16 mu seconds, we can later graph out a function that will show how much of the detectance change we can have per how close our detectant has to be to the capacitor, which is given right here. And as we see, which is very obviously demonstrated in this graph, our detectant must be very close to the capacitor, basically touching it, which is good because that's what we want, since we want to detect a touch on our capacitor. And we see that as the distance is decreased, so as our finger is more and more closer to touching the capacitor, we see that we can detect a less and less negative change So basically a more higher value of change and more precise value in our calculations. So basically our sensitivity of the capacitor becomes more and more well defined once our finger becomes closer to the capacitor. And as we see here, this is shown in this chart here, which we're sending out. We have nothing being pressed, and as soon as we press capacitor 1, which is outlined in blue, we see that the time constant, basically the time, increases dramatically, and we are now very obviously able to detect this finger touch, and thus from there send in output for a W key press. And this repeats for capacitor 2, 3, and 4, which will now be shown in our live demonstration.
So on screen currently, we can see the values of the 4 capacitive touch sensors. On the left, we have the W touch sensor. So that is corresponding to the W key. And then to the right of it, we have the A touch sensor. To the right of that, we have the S. And finally, we have the D. And I am pressing the touch sensors, and you can see the values increasing. We can also see the graph output if I go to the serial plotter. And we see that if I let this clear, you can see that the values are pretty erratic and they're also very low. This is in comparison to when I press the graph. These would be our fringe fields, and this is where the actual graph is. So in comparison, the fringe fields are pretty much negligible. And you can also see that all of the values are approximately the same for the W, the A, the S, and the D keys. There we go. And they're all around that same time.
Okay, now I'm gonna give a demonstration of playing Tetris with the capacitive touch controller.
And lastly, here are references. Thank you very much for taking a look at our project, and hopefully not all of it was wrong.